And we are continue our lesson by interchangeability, standardization, and technical measurements. Our theme numbers 2, size tolerance, joints, and fits. And I want to show to you some videos about size tolerance, about joints and fits. And first video that I want to show to you, it's introduction to the tolerance.
In this lesson, we're going to introduce you to one of the most important parts of your engineering drawing, tolerances. In fact, these tolerances are why your drawing exists in the first place,
Intro
to make
to
sure we
tolerance.
communicate exactly what is required for this part to be manufactured or inspected.
And what is a tolerance?
So let's first
discuss
how we may think of
perfect
parts in our head.
parts.
And usually we think of them as perfect shape, sizes, things like that. In fact, our CAD models are designed in the part's perfect state, exactly in the ideal way we want them to be. However, there's a truth about perfect parts. They don't exist. Consider how parts are made. No part will ever be made absolutely perfect. If you have any interaction with your production or inspection process, you know this to be true.
So no part will ever be absolutely perfect. It's very important.
A part may look perfect at a macro level, but a micro view could show many imperfections. So in the case right here on this machined surface, the surface may look flat. However, if we took something called a profilometer, which is a device that measures surface roughness, and measured the surface, we would clearly see that it is not. In fact, if you ran your fingernail across the surface, you'd probably notice bumps and ridges. It's not a perfect plane. Perfect parts are also unattainable due to things like improper tool usage or worn tools, machining errors, programming errors, material stresses, inspection methods, employee skill levels, environmental conditions, or many other things, including just sometimes bad luck. So how do we define what level of imperfections are acceptable? For example, holding your phone in your hand, you can see that it has probably a width, a height, and a thickness. But how wide is too wide for them to have a repeatable process on their phone? Or too tall, or too thick? What is the tolerance on those dimensions that would be acceptable, that if they produce that part at the end of the day, they can accept it? Well, we dictate how much we can accept with tolerances. A tolerance is the acceptable range of dimensional variation that still allows for proper function of your part or assembly. The variation defines the maximum and minimum limits for the dimension, geometry, or any other limits that we have to set on the part. For example, we know the diameter of this shaft isn't perfect, even though it shows it to be in the CAD model. What we would have to do is apply a tolerance to control the diameter to make sure that it properly functions when it gets into its assembly or when it gets to its final operating conditions. We do that by putting dimensions on our parts like this. Now, this still does not have a tolerance to it. To start, we are just saying that the perfect or the ideal would be this 3.585. But we still need to know what is acceptable here. Here are some examples of ways that we're adding tolerances now to our ideal part. We're showing what is functionally acceptable, or what the manufacturing limits are for this diameter. These are several tolerancing methods that we will be discussing later, but it's important to know that we're putting limits here on this part. Now we know what is acceptable here.
And the next video about tolerances. Why use tolerances?
Let's discuss why we use them. All dimensions must have a tolerance at some point in a manufacturing process.
All dimensions must have a tolerance at some point in the manufacturing process.
In fact, there are many benefits to having these tolerances. The first is to just communicate the manufacturing limits of your part. For example, we have this tolerance here placed on the width of this part. We would have a 0.5 total length tolerance, plus or minus 0.25, on this part that is 20 inches long. This clearly communicates what the target is, which is 20 inches, and where the outer limits would be, 19.75 and 20.25. It's important to have this information so that when the machinist makes this part and they go to inspect it, they know if it's acceptable or not. Next, tolerances help convey critical dimensions on our parts. Let's consider this pocketed feature right here. Without a tolerance, we have no idea how important this dimension is, especially since we don't know what the limits need to be. What is the manufacturing process that we have to use here? Can we drill it by hand? Does it need to be reamed? When is this hole too big or too small to not fit the application? Is our customer going to reject the part? Is our supplier going to use an extremely expensive method to produce this when maybe it's not that important? Well, now when we give it a tolerance, we can determine how important this feature is and how we need to manufacture it. Looking at this tolerance right here is an extremely tight tolerance. We can only go from 0.8742 to 0.8746. That's very hard to hold. In this case, it dictates that the part is probably going to cost us more to manufacture because we have to use some sort of specialty process. It also tells us, though, that this is functionally critical and may be used for something like a press fit. We now know this dimension is important and need to treat it as such in the manufacturing process. Tolerances, most importantly, ensure assembly with other parts or fit and function. For example, if we have this yellow and green part right here, without tolerances, there's a high probability these parts will not fit together if we can just make them however close to this 0.250 that we want it to be. We can make this yellow part just slightly too big and this green part just slightly too small, and now they won't fit together at all. Now, if you receive this part on your print, you may not have information on the other part. So you need to know what the manufacturing limits are to make sure that this part can be approved, and therefore, when it gets sent into assembly, will assemble together properly. We can always ensure these parts fit together if they have proper tolerances. Now, we won't go into detail too much on why these will always fit together, but as you can see on the yellow part, it can't ever get larger than 0.250. That is the upper limit. And for this green part, the hole can never get smaller than 0.251. That means that no matter what, these two parts will always be able to fit together if the proper tolerances are met. It is the responsibility of design to make sure that these two parts will go together, but it's information that they are conveying to the person reading the drawing to make sure they make the part correctly so that later on in the assembly process, they don't have a major issue. Finally, from a legal standpoint, tolerances define the acceptance criteria for part inspection. Remember, these drawings are contracts, and in many cases exist between two different companies. If a company cannot properly meet the tolerances, they are not able to fulfill the order that has been provided with the drawing. So these tolerances determine the difference between accepting and thus paying for the parts and rejecting the parts completely.
And types of tolerance.
Hello friends, today we will learn types of tolerance used in manufacturing process.
So, tolerances. Tolerance can divide by dimension tolerance and geometrical tolerance. Geometrical tolerance, we will discuss it later. And dimension tolerance divide into unilateral tolerance and bilateral tolerance. The difference between upper limit and lower limit of subject dimension of the job is known as tolerance. The zone between upper limit and lower limit is known as tolerance zone. Actual size must lie in this tolerance zone, dimensional tolerance. The tolerance given to control the dimensional feature is known as dimensional tolerance. Unilateral tolerance, one lateral side. The tolerance zone always lie above zero line or below zero line. In case of unilateral tolerance, one side tolerance. Below zero line examples: low limit, upper limit, and tolerance zone below zero line. It's tolerance zone. Second example, zero line, lower limit, upper limit, tolerance zone, again below zero line. It's tolerance zone. And unilateral tolerance above zero line examples: zero line, lower limit, upper limit, and tolerance zone above zero line. Next example, you can see a lower limit and upper limit of dimension, and tolerance zone, green tolerance zone, again above zero line. In both the cases, tolerance zone line lies above zero line. It means plus deviations only. Bilateral tolerance, B2 lateral side. We have lower limit and upper limit, and tolerance zone above zero line and under zero line in the same time. In both the cases, upper deviation or lower deviation will not be zero line, and always will be a combination of plus and minus. The tolerance zone always lie on both sides of zero line for bilateral tolerance, above zero line and below zero line. It is not necessary that zero line will divide tolerance zone equally on both sides. It may be equal or unequal. Fundamental deviations for holes, we use J, JS. For shafts, small j, JS, denotes bilateral tolerance. And the last video that I want to show you, it's video about fits. Types of fit.
Clearance fit. In this video,
Clearance
we
fit.
will about clearance fit. The clearance fit for the boss is regarded as a shaft 30 millimeter hole. A hole is defined as the member which houses or fits the shaft. It may be stationary or rotating. A positive
can see clearance.
exists between the hole and the shaft. It is obtained by selecting the maximum and minimum limits of the shaft and the hole. Interference fit. In this video, we are going to see about interference fit. Consider a bolts pressing machine. Hub. Pressure gauge. A fit between two parts in which the external dimension of one part slightly exceeds the internal dimension of the part into which it has to fit. Fastening between two parts, which is achieved by friction after the parts are pushed together, rather than by any other means of fastening. The hole diameter is smaller than the bolt diameter. It is an interference fit.
Interference fit.
Transition fit.
And third
This
type
video
of
we will
fits,
see about
transition fit.
Hole. Shaft. Hammer. For example, by hammering, insert the shaft into the hole and fix it. When the dimension of the hole and the shaft such that there exists a positive clearance when the shaft is fitted into the hole is known as transition fit.